near future, your options probably will steer you towards approaches that will make use of single precision, even if that means doing, sort of some kind of mixed precision algorithm. Only the highest, the highest cost and high-end discrete GPUs that you buy for clusters, they're the only ones that currently have the really fast double precision performance. So this should guide your thinking as you ponder these different algorithms. If you have a choice between single and double precision, think about where you expect that code to run. Is it going to run on somebody's laptop? They probably will only have single precision hardware that's fast. So that's something to keep in mind.
You use the version number of the one where you have the double precision option of the code?
I'm sorry, say that again?
You know the versions, the Tesla, whatever.
C2050? So the C2050 is the Fermi, Tesla C2050 is the Fermi high-performance computing card. That's the one that basically has the peak performance double precision hardware. The gaming-oriented version of the same hardware is called the GTX 480. And so those are the cheaper video game cards. The difference in price is about a factor of 5, roughly, maybe 4.5. So it's a factor of 4.5. The professional cards have error-correcting memory. They run at a slightly lower clock rate, so in terms of absolute peak single precision performance, the professional cards are slightly slower, but part of the reason for that is they're going for higher reliability. The video game cards, companies like NVIDIA and AMD never even see those video game cards. They're made overseas and where labor is inexpensive, and they're able to fabricate those things at low cost. These companies never even look at them. All the quality assurance, whatever there is that's done, is done by those companies that actually fabricate them overseas. So in terms of reliability, the types of GPUs that are in a laptop or in a video game type card, they don't undergo anywhere near the same quality assurance testing. And so if you get a wrong answer once in a while, well, they're sold as video game GPUs. If you get a blue pixel where it was supposed to be red, and it's in the middle of a video game, it's only there for a 30th of a second, and they figure nobody will notice. So that's something to be concerned with. If you're going to run a big job on a cluster for weeks and weeks or months at a time, you may be much more concerned about whether you're running on a professional GPU or a gaming-oriented GPU. But for developing software, unless you're heavily concerned with double precision, the gaming cards are perfectly fine. So, we do a lot of our development on the gaming-oriented cards in our desktop machines, but, we just run on the more high-end cards. So you've seen this plot probably 1,000 times. The blue line is CPU performance, the green line is the GPU performance, and this goes up to the old generation GPUs. It's actually a bigger gap now. So that's the arithmetic performance. The important point to note, basically, is that the arithmetic performance is following Moore's law, so it's approximately doubling every 18 months. And they're likely to be able to sustain this because in the case of both multi-core CPUs and in GPUs, they're just doubling the number of transistors every 18 months, and even if they can't clock them at a higher rate, they can have twice as many cores or twice as many of those streaming processors every 18 months. And so that means you, as an end user, will get about double the arithmetic performance. So that's great news if your code is arithmetic bound. The bad news, and one that they may not talk about much, is that memory bandwidth is not increasing at anywhere near that rate. Memory bandwidth is basically going up at a linear rate. With modern GPUs, there's a ratio, if you compare those two performance levels, in the time it takes for you to read a single precision floating point number from memory, you can do, forgetting about latency, just the bandwidth we're talking about. In that time, to fetch one floating point word, single precision, you could do 40 arithmetic operations. So what that tells you is when you're writing your GPU code, you're thinking about the math, like if you have choices of different mathematical algorithms. A lot of people, myself included, were taught in the old days to avoid doing arithmetic at any cost. With GPUs, the world is upside down. Arithmetic is practically free. You can do floating point arithmetic. Don't try to avoid doing floating point arithmetic. It's very cheap. And it will get cheaper and cheaper and cheaper because of Moore's law. What will not get cheaper is reading data from memory. So what this should tell you is you have to, it's a delicate balance. So there are cases where right now it's not as clear cut as it could be. There are cases now because the GPUs have caches, you can get away with things like very small lookup tables. If you have a very small lookup table and it fits in those on-chip GPU memories and caches, you might be able to use a lookup table approach for an algorithm that might be the traditional way. Because on CPUs, lots of people have designed algorithms that use lookup tables and things like this to avoid doing arithmetic. But if your lookup table gets to be too big, then that ends up hurting your performance because you're going to be limited by this memory bandwidth, not by the floating point arithmetic rate. So this is something to be aware of, and the people that give lectures over the next 2 days will probably make an effort then to point out why do it this way versus another way. Well, sometimes it's just related to these ratios or the way that code maps to the hardware. So some of the example applications that people, not just our group, but many groups, have ported to GPUs include molecular dynamics, just to name a few. There's NAMD, AMBER, OpenMM, Romax, LAMPS. I think I saw DL Poly has a GPU version. So practically everybody either has or is working on a GPU-accelerated version of their molecular dynamics code. There are several quantum chemistry packages out there that have sort of GPU versions that are in development. I think the games team has one. The Martinez group has a new code they call Terrachem that's totally GPU-based. And there are a few others that are floating around here and there that are probably in some state of development. A bunch of the docking codes, I've heard at least 2 or 3 different versions of Autodock. So people have taken the Autodock code and accelerated that on GPUs. VMD and others are starting to use GPUs to speed up various parts of the molecular visualization. I'll tell you more about that later this week. Analyzing molecular dynamics trajectories, building the structures prior to simulation, adding ions, things like that. And then on the workshop website, I've actually put a copy of a paper we just wrote, a little mini review that sort of covers a broad range of these things in a shallow amount of detail. So if you're curious what's been done or where things are, this is available on the workshop website. So NAMD is a program that Jim works on. It's our molecular dynamics software, and it's a recipient of the 2002 Gordon Bell Award. There are several thousand users of NAMD, and it's one of the first things that we applied GPU acceleration to. Just to give you an example of the sort of speed-ups that you get with something like NAMD, with the older version of NAMD, the speed-up is about a factor of 12 per, so adding 1 GPU is approximately equal to adding 12 CPU cores. So if you had a hypothetical cluster node that just had 1 CPU core, and you added a GPU, that'd be like having 13 CPU cores. And so you can see various levels of the runtime for a 1 million atom virus simulation on differing numbers of GPUs and nodes. And Jim will tell you all about this stuff in his lecture. And he has a new beta 3 of NAMD posted online now that people can test and play with. And if you have any questions, you've got him cornered. And so I work on VMD, which is our molecular visualization and analysis program. And just to give you an idea, some of the areas where we've applied GPUs, one of the first things we used GPUs for was to accelerate calculation of electrostatic fields. And the first application that we used that for was in building structures. So in those very large structures like the virus simulation or the ribosome, where you have nucleic acids, when you place ions, it's very important that you put them in the right spot. Otherwise, as the simulation begins to run, they get stuck in places where they don't belong, and it causes you to get a bad simulation. And so this was one of the first things we used it for. And in this case, we wanted to compute very high-resolution electrostatic field maps. And I'll be talking a little bit about the algorithms for this tomorrow. We've also used GPUs to accelerate calculation and display of molecular orbitals, basically evaluating electron orbital amplitudes on a 3D lattice. and then using that lattice to compute isosurfaces that are then displayed on the screen. In traditional software, this, even for a very simple quantum chemistry simulation, this might take up to a minute for a large structure like a carbon-60. With the GPUs, we're able to do this over 100 times faster, and so we can actually animate these things. Up until now, in order to animate something like this, we would have to pre-calculate these grids of electron overlap amplitudes, save them to disk or load them in memory. It might take hours to do this ahead of time. And then once we would have done something like this, it is what you've calculated. You couldn't interact with it. You couldn't change the parameters. And so having the GPUs has really given us an opportunity to make those features more interactive so that you can just basically pull a slider or change a selector or toggle switch on the way it's displayed or the particular orbital that you're calculating, and it happens as rapidly as any other molecular visualization feature. So that's been really exciting. And then various others. So the key thing that we've been interested in doing with VMD at least is, the speed of large supercomputers and, of course, the impact of GPUs on molecular dynamics itself is putting more and more pressure on the visualization and analysis needs. And, of course, the laptops that all of you have or your desktop machines at work, those are sort of the most compute-constrained platform that exists, because there's really no way to add hardware to one of these laptops. It is what it is. And so if this is what you use every day, the only opportunity we have for increasing your computational power is to basically make use of your GPU, not just for drawing, but also for crunching the numbers. So for laptops, that's a huge deal. And of course, for desktop machines, if you're analyzing long molecular dynamics trajectories, as those things get bigger and bigger and bigger, unless you either have access to a cluster at your own institution to do those analyses or elsewhere, having the GPUs in your desktop machine for some of these things, we can make those analysis jobs run tens or hundreds of times faster. So that's really an exciting opportunity for us. Another interesting aspect of GPUs, not only do they make your calculations faster, but if in the best cases, they also reduce power consumption. The predictions are that in the next 5 to 10 years, the cost of the machines that we buy, these supercomputers and clusters, will not end up being the dominant factor. It will end up being power consumption. Already, the cost of a machine, a big cluster or supercomputer's power consumption is equal to the price of the machine, and that's right now, over a 5-year period. So if you buy a $200 million machine today, and you run it for 5 years, you're paying $200 million for the machine and then about $200 million for the power. So this is very scary if you're in the business of running really big supercomputers. So there's a lot of interest right now in the supercomputer industry in finding ways to make machines more power efficient, because of course they would much rather spend the money on getting faster machines and not feeding the coffers of the power companies. So to give you a simple example, running a small electrostatic field calculation at time averaged over a trajectory for about 700,000 atoms, running on the CPU on a single node, I believe, it's a single node of the NCSA cluster. So that's 4 CPU cores, takes 1,465 seconds at 299 watts through the entire run. Doing the same thing using 4 CPU cores and 4 GPUs, we get it down to 57 seconds at 742 watts. And if you divide out the difference in continuous power consumption over time, the integral of that power over time, we get it. So we're getting a 25x speed up and about a 10x increase in power efficiency. And so that's a big deal. If we end up being power constrained in a few years, GPUs or GPU-like devices may be the answer. At least for algorithms that are very arithmetic heavy, like the sorts of things that tend to run well on GPUs. And so this was observed before for things like the Los Alamos Roadrunner machine. But going forward, this is probably the only way we'll be able to build really big supercomputers. And so that's it. So next, who's our first volunteer? First of all, are there any questions? Does anybody have any questions about anything I said up to now? Yeah.
I was curious if you had sort of an accelerators of PDAs, and one view is PDAs down the road will plus or minus?
So I'll tell you my opinion, and